Welcome back to my channel. This video is about ultimate strength design of beams. But before solving problems, it's important to know the notations and symbols to be used. I hope that you will learn a lot in this video. Principles of reinforced and pre-stressed concrete. For this discussion, I'll be discussing course outcome 2, and course outcome 2 includes ultimate strength design of beams, bar cutting and development length, and shear in beams. So we are done with our previous discussions, which was working stress design and pre-stressed concrete, or concepts of pre-stressed concrete. What we will do is now compute design strengths, which are incorporated with your USD, or ultimate strength design. So in order for us to effectively compute and understand analysis and design of USD, it is important to deal first with the notations and symbols to be used in this type of design, which is USD. To start, the notation and symbols used starts with your alpha, which is the depth of equivalent stress block. So if we will remember, or if we know our concrete, so before in WSD, if it cracks, automatically your neutral axis should be, if it's a crack section, is within the crack of your concrete, and above that would be your concrete that shoulders compression, and then below that is your reinforcement that caters tension. In here, what we do is later on we would realize that when your concrete is crashing, the area of the concrete above has a slight difference, or is floating above your neutral axis, in which the neutral axis, when drawing your stress block in here, and then this is your tension, this is the one in compression. So we would know the values later, but right now let's just change the shape of my stress diagram or stress block. So in here, this is what we are describing, which is the depth of the equivalent stress block alpha. Similar to this, or taken from this, from the tip of my concrete fiber in compression to the neutral axis, it's still my C. Later, we will term that as the depth of your neutral axis. So I hope that could be part of your new learning, in which alpha now, or letter A sometimes is being used, would be always measured in millimeters. That is the depth of your equivalent stress block in ultimate strength design. Also, what we have here is just a review of your gross area of section. The gross of area of section is measured in square millimeters, and then that's the area of your concrete plus the area of your steel. To review or recall, the area of your concrete is A sub C, which is also termed as your gross area, measured also in square millimeters. AS is again the area of your tension reinforcement. So from time to time, if we see AS, always, whether it's reinforced singly or doubly, A sub S would be the area of tension reinforcement. Since there are times wherein we would encounter that your reinforcement is doubly reinforced, meaning your section is DRRP or DRB, we will term the area of compressive reinforcement as AS prime. What does it mean? In WST, when looking back we are trying to analyze or design your singly reinforced. And then as provided by NSCP, there should be hangers on top. But these two are not actually bearing any stress in the analysis of our section. What we know is that this is shouldering the one in tension and the above is in compression. Again, assuming that the two on top is just your hanger. In cases wherein your rho becomes greater than your rho maximum, so it doesn't make sense as of now because we don't know what's rho maximum, but please remember that I've mentioned if your rho is greater than rho max, what happens is your section now should be designed and analyzed under double reinforcement, meaning there is area of steel bottom and above that is shouldering tension and compression accordingly if this is, for example, my applied moment. So again, assuming that my rho becomes greater than rho max, in which does not make sense as of now because we don't know rho max, but let's just put it this way, na kulang yung reinforcement sa baba, kaya kailangan mag-reinforce pa ako sa taas. This would be termed as your AS. Again, because this one now is withstanding compression force from your moment, this is my AS prime. If we will change the orientation of your moment, let's say, I'll just erase. Let's say this one becomes different. Now, ang nangyari is naging negative moment siya. It's coming from this up to that. This is your moment, tension at the top, compression at the bottom. This would be automatically become your AS, and this one is your AS prime. Why? Because by definition, AS should be the area in tension for reinforcement, and AS prime would be the area of your compressive reinforcement in DRRB. Again, it only happens on a doubly reinforced rectangular beam or a doubly reinforced beam. All areas are measured in square millimeters. The width of your compression face member is still termed as your B or small b, which is millimeters, in millimeters. Your C, as mentioned before, would be the distance from extreme compression fiber to neutral axis, also termed as the depth of your neutral axis. So sometimes that would be the one used to determine or to describe C, depth of neutral axis or distance from extreme compression fiber to neutral axis, as mentioned and discussed before. D is still the distance from extreme compression fiber to centroid of reinforcement or tension reinforcement in particular. And this time, we have your D prime. In case there are times that the reinforcement are now considered on top, drawing or withstanding compression forces, therefore it would become DRRB. What does it mean? Before, pag SRRB or SRB, this is your reinforcement at the bottom. We call that as AS. And then automatically, the centroid of that will be measured from this top to be equal to D, which is the effective depth. Now, in case it becomes DRB or doubly reinforced, what we do is we have now to compute also for the area of your steel in compression. The centroid of that would be measured to be your effective depth prime or D prime. D sub C would be the thickness on concrete cover measures from extreme tension fiber to centroid of bar. So before, if we will provide here your stirrups, let's say may stirrups ako dito, tapos the tip of the stirrups up to this tip of the concrete would become your concrete cover. Pero sometimes, D sub C would be given. It measures from the centroid of your tension fiber up to the concrete cover. Okay? Ito siya. The centroid of your bar up to the tip of your compression fiber. Sabihin, D sub C to. Nakita nyo, dun sa centroid ng mga bars ko, dito, tapos dun sa dulo ng tension fiber ko, that's my D sub C. What does it mean? If I will call this as my H, no? Therefore, my effective D from the illustration would be equal to H minus D sub C. Okay, from the geometry, we can say that the effective depth D is equal to H minus your D sub C. D sub C again is the thickness on concrete cover, measures from extreme tension fiber to center of your bar or wire. Okay, so there are times that D sub C is given, and then it would be easy for you to compute the effective depth provided that your overall depth is given, which is H. E sub C is similar to what we have discussed before, which is the modulus of elasticity of concrete, can be measured two ways. One is 4700, the square root of Fc prime, or it could be equal to Wc, or the weight of your concrete, multiplied by raised to the 1.5 times 0.043 times lambda multiplied by Fc prime. Remember that lambda has two values, either 1 or 0.75. When does it happen to be 1? When is for normal concrete, or if the weight of your concrete is not specified, we assume it's normal weight. It's 0.75 if it's lightweight material or lightweight concrete. So that's your E sub C. Next is your E sub S. From the code, the modulus of elasticity for steel is assumed to be equal to 200,000 megapascal. Just a review, and we have already mentioned that on our previous discussions. F sub C is the unit compressive stress in concrete, measured in megapascal also. Recalling Fc prime would be the specified compressive stress in your concrete. Megapascal is the unit. Mostly, it is done by a laboratory or by testing on the 28th day. Okay, because on the 28th day, it is assumed that your concrete reached its maximum compressive stress. F sub S is before all just given to us, di ba? Ginagamit natin yan when we are computing for your stresses. Pero now, we will term it specifically to be calculated stress in reinforcement at service load. When we say calculated, there is a formula that we will derive in order for us to compute for F sub S, which is the actual or the calculated stress in reinforcement. Accordingly, we have your Fy. I think this would be the moment that we will utilize your F sub y, which would be your specified yield strength of steel, measured in megapascal. In balanced condition, your Fs, if not given, is assumed to be 0.5 Fy. Okay, just remember that. Continuing, as mentioned a while ago, we have what we call your H, which is the overall thickness of member, or if we're pertaining to walls, it would be the unbraced height. But this time, because UST discusses in beams, tapos girders maybe, that would be the overall thickness of the member. Yan yung tip-to-tip distance or depth. IG is the moment of inertia of gross concrete section about centroidal or local axis, neglecting reinforcement. And INA would be the moment of inertia of reinforced section about centroidal axis. If we will take a look on a cross section of a concrete, let's say base by H, pertaining that this would be our reference line, this is X or this is Y, we can automatically say that IG, or the gross inertia, would be base by H cube over 12. On the other hand, INA would be pertaining to the moment at neutral axis or to the centroid, which is the global centroid for this figure would be here. So what do? We transfer your moment of inertia to that position, which is a d squared. So simplifying this equation would yield, if my IG is already computed to be BH cubed over 12, what's the area of the cross section? Base by H. Tapos ang distance ko from this one up to this one, because that's what I'm measuring, it would be H over 2. So it's H over 2. I'll square it, and then simplifying this term would yield to a value of B H cubed over 3. So that's the difference between your IG and your INA. Be particular that IG here would be I sub x, no? I sub x. Kasi that's one, we are rotating at the x-axis. If it becomes I sub y, just review lang, the base becomes your H, the height becomes your base, over 12. And then we can compute INA also for in relation to your y-axis. Dito, pwede natin tawagin IX at neutral axis. But because that's the orientation, we can just denote that it's INA and this one is IG. So I just want to review you or to inform you of the possible values of IG and INA. So much for IG and INA. Let us continue with the rest of the notations and symbols important for the analysis and design of ultimate strength design. What we have here is your M sub n, which would be the nominal moment measured in Newton millimeter or kilonewton. M sub u is the factored moment at section Newton millimeter, or unit could be kilonewton meter. E sub c is the strain in concrete. Since from the code, concrete is assumed to crack at maximum 0.003 strain. So we will term your strain in concrete to be E sub c. On the other hand, we have your factor beta 1 that has been discussed or introduced to us. So that's the factor defined in section 422.2.2.4.3, in which your beta 1 could have three values: 0.85, 0.65, or transition 0.85 minus 0.05 times FC prime minus 28 for 2015 over 7. Remembering that if it's 0.85, therefore your FC prime ranges from 17 to 28. If it's 0.65, FC prime is greater than 55. If it's this equation, it should be within 28 but less than, or greater than 28 but less than 55. Just a review of your beta 1 value, because we already have discussed that in pre-stressed concrete on why the values are like that. On the other hand, if you have E sub c, you also have your E sub d, or the net tensile strength. Later, there will be a lot, or the next discussion, I will be having, or we will be having discussion of your strain diagrams. So yung aking mga strain in concrete and steel sometimes changes in values in order for us to derive equations and symbols that would help us analyze and design our sections. ETY on the other is just your net tensile strain, but this time it would be a yield point. In here, it's particular that it's Fy over Es. The key point here, or the key word here, is yielding. That's why we use F sub y. Therefore, if I go back to E sub t, this is automatically your Fs over your Es. Kasi there are only two values for your stress in steel. Either it's actual or calculated, or it is the yield point, which is Fs or F sub y respectively. So those values would play a big part later as we derive values and relationships between our symbols and notations. Your raw is just a review of us. Here, raw is AS over BD, which is the area of your steel over the area of your concrete, which is space multiplied by its effective depth. So sometimes, once we discussed your basic internal forces and then we discussed your derived equations under ultimate strength design, there are ways wherein you can use your derived equation, but you need to compare your actual tension reinforcement or steel ratio on other values. So that's why I am introducing this to you, because there are alternatives in solving or analyzing your reinforced concrete. Meron din tayong other ways or alternative in designing it. So ang atin major 2 division would be using of basic, which is compression equal to tension, and number 2 would be your derived equation. So we look forward in knowing what's basic means and what's derived equation means. Your raw balance is to be compared with your raw. So here, what we do is we apply our future understanding of the derived equation in order for us to solve or analyze and design our reinforced concrete. But here, if raw B is your balance steel ratio. Under balance condition, your steel and concrete yields at the same time. So next is your reduction factor. So there are 2 values for reduction factor. If it's just reduction factor, what we do is reduction factor, or on the other, it would be strength reduction factor. Pag reduction factor lang ang tawag, or RF, it would be your 2001 provision. And then if it becomes strength reduction factor, that's your 2015, which is the latest code. What does it play, or why is it important? If I have my nominal moment, M sub n, multiplied to my phi, it would yield to my ultimate or factored moment, which is the design moment. So ito, pwede itong tawaging design strength. Ito, pwede itong tawaging design strength. Because here, in RCD, ultimate strength design, we already incorporate factor loads or load combinations. So what we do is we need to make sure that we are conservative in such ways. We become conservative when we induce your strength reduction factor under 2015 provision and phi as a reduction factor under 2001 provisions. So again, your phi is for conservative measures kasi you don't want, you make it safe in such a way na nagkakaroon ng allowance, no? Yung for example, yung nominal moment mo computed could actually be equal to 100 kilonewton meter. But because of reduction factor, assuming it becomes phi equal to 0.9, therefore your design strength, or the one that you will let your member withstand, would only be equal to 90 kilonewton meter. So it becomes conservative on the end of a structural engineer. How did we come up with phi equal to 0.9? On the next discussions, we would realize and we would understand what these values are or how these values are determined. Okay? Next is your dead load, live load, and earthquake loads. Because of load combinations that we will be using for this quarter, if D, or your letter D, capital D, stands to dead loads, L stands to live loads, and E stands to earthquake loads. And these loads are combined together and then multiplied by a certain factor, which we call your load combinations, in order for us to yield your factored loads. No? Yung factored loads ko na yon induces or produces your ultimate moment, and your ultimate moment could be the basis, or your ultimate moment is actually the basis of your design. So, yung sa analysis, ang kinocompute yung MU. Sa design, ang ginagamit is yung MU para makapag-design tayo ng section or geometry of your reinforcement, both for concrete and for your tension. So, medyo madami pang notations and symbols, but this would be the summary that we could use for this term, and understanding them or being familiar with them is helpful in dealing with our next discussions. Would be on my next video is provisions and assumptions of ultimate strength design. We would now understand what are the things that we need to remember when we are designing slash analyzing uh, reinforced concrete under USD. Okay, but this time, this is particular to beams. Thank you for watching and see you on my next video. God bless.